Hey guys, good afternoon. Today we are going to finish up our notes dealing with tangent lines. I hope you did watch that video sometime yesterday. If not, I definitely still want you to go back and watch it because tangent lines, again, first you do need to know how to do it, and I'll do a warm-up just to remind yourselves how to do it today. But then we're going to be looking at applications of the tangent line to kind of finish up our notes. So yesterday, hopefully, when you watched those videos, we talked about how we could find a tangent line. And basically, we're looking for the actual equation of the tangent line to a graph. And I like saying this is basically combining stuff you did in Algebra 1 with stuff you do in calculus. So we know how to find the derivative, which is giving us the slope, and then we know that how to write the equation of a line because you've been writing the equations of lines since Algebra 1. So just to review and make sure we're all at least starting on somewhat of the same page, I don't know if I shared this with you, I don't think I did, but I did just want to do a quick example of finding the tangent line. So when you have a question that says find the equation tangent to a certain f of x, there's two things you need. And I always like thinking about it is when you do a tangent line, the two things you need is a point and you need the slope. The point's going to come from the original function, and then we know that the slope is going to come from the derivative. It doesn't matter which one you find first. I'm going to go ahead and find the point, because that means I don't have to do any derivatives yet. So I can go ahead and plug that x value into my function. So I have plugging in pi over 3 in for x. And so I have 2 times the pi over 3. Pi over 3, thinking about our unit circle, the sine of pi over 3 is root 3 over 2. So simplifying it, not the prettiest looking y value, but we have pi root 3 over 3. So then we can also go back and find the derivative. We know that the derivative represents the slope at the tangent line. So if I find the derivative and then plug in the x value, that would be the actual slope at that coordinate. Any derivative rule we learn can be used. This one is 2x times sine, so we do need to use the product rule that we learned on Monday. So doing the product rule, I have the first times the derivative of the second plus the second times the derivative of the first. Again, order doesn't really matter with the product rule since you're just adding and multiplying. And then if I want to find the slope at that point, I can go ahead and plug in pi over 3. So I'll have 2 times pi over 3. I'm going to do some shortcuts. The cosine of pi over 3 is just 1/2 plus the sine of pi over 3, the root 3 over 2 times 2. So simplifying this, see some 2's cancel out, 2's cancel out. The slope ends up being pi over 3 plus the square root of 3. I know some of you are bothered by that slope because it's an expression and kind of ugly looking, but we can just use that as the slope. So when I want to write the equation of the tangent line, we have y minus the y value is equal to the slope times x minus the x value. The x value we have the tangent line at is this pi over 3. The y value was at pi root 3 over 3. And then the slope is this expression, pi over 3 plus root 3. I often don't simplify my tangent line. I know you're probably used to writing the equation of lines in slope-intercept form. I tend to just leave mine in point-slope form so I can avoid having to distribute and move things over and isolate y. But this is the tangent line. And I did want to remind you again, that is the actual equation of the tangent line. We won't often graph it. I did just because I had the time. And so basically, that red graph is the f of x, and then that blue graph is the tangent line that we just found. So we can see that that is the tangent line at pi over 3 to kind of put some context into what you're finding. Any questions on that problem before we look at some applications of the tangent line? All right, so first example I want to look at is a question that says, where does this function have a horizontal tangent line? So a horizontal tangent line, this is going to be probably one of the most common things we will do actually in calculus. I kind of make a joke of like, if you don't know how to do a problem in this class, like find the horizontal tangent lines, because that would be often what you want to be looking at. And so there's two parts to this question. We have to kind of think about like, what does it mean when a function has a horizontal tangent line, and then actually like find that horizontal tangent line. So in terms of calculus, when I say horizontal tangent line, how can I translate that into more of a calculus statement? What would that mean? The derivative is equal to 0. So if you see find the horizontal tangent line, that basically means you want to find when y prime is equal to 0. So we do need to find the derivative. Again, I'm going to offer you my advice. You can avoid it, but I think it's good advice. Whenever you see a problem written as a fraction, you could use the quotient rule, but I would always tell you to avoid the quotient rule if you can. So for example, if we're looking at this problem, this y right now is a fraction and it would require the quotient rule. You could do the quotient rule, but you have to think to yourself, so you have like this low d high, less high d low, all over the bottom part squared. And then after you find that first derivative, you're going to have to set it equal to 0 and solve for x. And the quotient rule does not make a nice looking expression. So I would actually recommend simplify y first, then find the derivative, and then use that simplified derivative to find your horizontal tangent lines. How can I simplify this one? If you have a monomial, you can divide each piece in the numerator by that monomial. You might be a little bit worried because you do see those fractional exponents, but we can make this a nice looking problem. So this first term is the same as saying 6x to the negative 3/2 plus, remember when you're dividing with the same base, you subtract the exponents. So like 5/2 minus 3/2 is just 2/2. Well, that's just 1. So really this second term is just the same thing as saying x to the first power. We're not finding when the function is equal to 0. We want to find when the derivative is equal to 0. So I can go ahead and find the derivative. Now instead of having to do the quotient rule, I just need to do the basic power rule or the general power rule. So 3/2 comes down in front. The 6 was already there. Negative 3/2 minus 1. 3/2 minus 1 is the same thing as subtracting 2 over 2. So it becomes minus 5/2. And then the derivative of x, that's a linear term. That has a slope of 1, so its derivative would just be 1. So my final first derivative, I have y prime is equal to kind of simplify it, well, negative 3/2 times 6. I can see that this is going to cancel out, so I'm going to have negative 9x to the negative 5/2 plus 1. So that is my derivative. That's like the first step. If this was a quiz or a test, you would earn part. Cool. This is real awkward. Quick question. How much of that did y'all hear?
I think you're about to say we could hear, like, you could get partial credit and then you stopped.
Cool. Okay. Teams is acting weird. So I'll just rewind a little bit. So we found the first derivative. On the AP exam, my quiz or my test, you will earn partial credit if you find the derivative. And then the rest of the points come from like actually answering the question. So if I want to find a horizontal tangent line, that is where the derivative is equal to 0. And so now we just want to use algebra to solve this. There's different routes you can take. Like I can go ahead and like subtract 1 from both sides, divide by negative 1. And so I have like 1/9 is equal to x to the 5 halves. I'm going to do it as 1 over x to the 5 halves because I just don't like dealing with negative exponents. Cross multiply, so x to the 5 halves is equal to 9. And then we do need to remind ourselves, how do we cancel out fractional exponents? Well, what cancels out a 5 halves is something to the 2/5. So I get x is equal to 9 to the 2/5 power. This would be the x-coordinate of a horizontal tangent line. Other ways you could write that, so a 5th root's the same thing as over 5, so this is the same thing as saying like the 5th root of 9 squared or the 5th root of 81. I would of course count all of those numbers as the same and give full credit. The big idea here is you want to just make sure that when you see horizontal tangent line, that means, big idea, find where the derivative is equal to 0. So we now know that at this x-coordinate, this particular graph has a horizontal tangent. Questions on that problem?
Do you have to solve for the y value also?
I'm going to be lazy, so the question does say at what points x comma y does this function have a horizontal tangent line? So yes, I probably should answer the question that I wrote. And so if I am solving this, again, we can leave things unsimplified in my class. So there's the x. How do I find the y coordinate? Is I can just plug the x into the original function. So like I could simplify this, you could simplify this. I'm not, because this would earn full credit on my quiz or test. That is the actual coordinate of the horizontal tangent line. Oftentimes, though, we are just going to be concerned about the x-coordinate. So that's kind of one application of tangent line. So we didn't actually find the tangent line, but we do know it's horizontal there. Another type of an example where we use tangent lines is an equation worded this way. So it says, find the equation of the line tangent to y equals 4x squared and parallel to the line 2x minus 2y is equal to 4. I did add this one later, so I don't remember if I distributed this problem to you. But some big ideas here that you have to kind of know. Again, tangent lines usually pull in together a lot of things you've learned in Algebra 1 with the calculus. So we're kind of reading through this, like I see find the equation line tangent, so that's a big clue, we're going to have to find a derivative. And then we have this line, 2x minus 2y is equal to 4. I know it's a line because x is to the first power and y is to the first power. And I want to find a line that is the tangent line that is parallel to that given line. Well, if I say that it is parallel, what do we in math know about lines that are parallel? Same slope. So we know that they have the same slope. That's really the big idea. And then the other big idea is we're talking about a line tangent, we're talking about the derivative. So like the big idea behind this one is we want to figure out when the derivative is equal to a certain slope. Well, right now the equation of this line is not in a friendly way to find the slope of it. That's not normally how we find the slopes of lines. So I would probably just go ahead and solve for y first. So I can go ahead and subtract the 2x and then divide everything by the negative 2. So I get y is equal to 1x minus 2. And what's important about this is this 1. This is the slope that we want to be parallel to. So again, what is slope in calculus? The slope is the derivative. So I can go ahead and find what my derivative is. 2 comes down in front, giving me 8, and that's going to be x to the first power. So we basically want to find now, well, when is this derivative equal to 1? So the equation we have, I want 8x to be equal to this particular slope of 1. Well, what x value is this going to occur at? This is going to occur at the value x is equal to 1/8. Visually, I think some of you who are visual, this will kind of help you figure out what you found. So 4x squared, if I just drew like a sample graph, we know that that is a quadratic. The line we want it to be parallel to is this 1x minus 2, which looks something like this. We want to find where a tangent line is parallel to that line. Well, we just found that the x value that's parallel to that is 1/8. And so we want to find the actual equation of the tangent line that would be parallel. And we don't have to be fancy about this. We really have everything we need to know. So the tangent line we know is y minus the y coordinate is equal to the slope times x minus the x coordinate. Well, the slope is clearly 1. That's what we just found. The x coordinate we also just found, that was 1/8. Well, how do I find a y coordinate? When I know the x coordinate is we can plug it into the original problem, 4x squared. So plug into the original problem, I have 4x squared. And again, you're allowed to be lazy and don't have to simplify your answer. So that is the equation of the tangent line. That is tangent to 4x squared and also parallel to the given line. Questions on that one? All right, I have one more type of example to do. This is College Board's favorite type of example to do when it comes to tangent line applications. And I usually call these just like the missing k value. K is the common variable they use, but sometimes they use like r, s, m, whatever. Typically they do use k. And basically it's going to be one where they give you the tangent line, but then the actual function is technically unknown. So we have this, we have the line of y is equal to 6x plus 4 is tangent to this graph of f of x equals to x squared plus k. And we want to find the value of k so that these two graphs are tangent. Now, yes, you could probably look at that graph and figure out what k is, but normally you would not have a graph in front of you. That's more just for the visual. Whenever you're doing a problem like this, it is going to end up being like two equations you have to write. Some people prefer to just have like this around, just like tell me the steps. Some people are more conceptual, so I'll kind of do it both ways. If you're the type of person that likes just having steps, you are going to create two equations. The first equation that you're going to write is going to be where the derivative of the function, and you're going to set that equal to the slope of the given tangent line. And again, conceptually, we know that makes sense. We know that the derivative represents the slope of a tangent line. So if I give you the tangent, then you technically know what the derivative is already equal to because you can clearly see it in the problem. And then the other equation, because you do normally have like a system of equations in a way, the second equation, the theory behind it is when you have a tangent line and a graph, they touch right here. They're touching each other, and when they are touching each other, they have the same x coordinate and they have the same y coordinate. If they're touching in the same place, that means they have the same y coordinate, so you're literally going to set f of x equal to the tangent line itself, not just the slope of it, at the x value where they intersect at. And normally that first equation, you'll find the x value, so you have something to plug into it. So I'm looking at this problem. This is my given line that I have. I can look in the problem. This line is y equals 6x plus 4. We know that that 6 is the slope, and I know that the slope is the derivative. So I know the derivative is going to have to be equal to 6. Well, what is the derivative? F of x is x squared plus k. The derivative of x squared is 2x. And then be careful with this. Yes, k looks like a variable, but k in this case is representing a constant. So what is the derivative of k going to be? 0. K is just a number, so we know that the derivative of k is just going to go to 0. So I have, this is my first equation. I have the derivative is equal to the slope. Well, if 2x is equal to 6, where's this tangent line happening at? This tangent line is happening at, not 6, but this tangent line is happening at 3. And then I can use this to say, well, at 3, the tangent line touches the graph, so they have the same x-coordinate and the same y-coordinate. So my other equation I have is that, hey, this function itself is going to have to touch the tangent line at a certain value. Well, what value is it going to have to touch at? It's going to have to touch at the x value of 3. So you can just simply plug it in. 9 plus k is equal to 6 times 3 plus 4, and then use that to solve for k. And you are allowed to be lazy like me and leave your k like that. Again, you will always have to have 2 equations because there's kind of 2 things going on. You have the part where you know the derivative is equal to the slope, and then you also know that the tangent line is touching the function, so that's where your second equation is going to come from. Again, I can almost guarantee you'll have a question like that on the multiple choice part of your AP exam, which also means you definitely have a question like that on your quiz. Any questions on that problem? Cool. So your assignment, that's going to be it for notes. So we have homework 4, which was your basic derivative rules. Again, you're only doing multiples of 4 of those. The answer key does have more problems answered if you want to go back and do some more for practice. Homework 5, which is your product and quotient rules. And then this homework 6, which is going to be tangent lines. Your quiz, so this is a longer unit, so we do have a second quiz. It is on Tuesday. Tomorrow will be a day to kind of work and get stuff done. I'll probably have like a warm-up, and then you'll have the rest of the period to work and complete stuff on your own. And then same thing for Monday. It will be like I might have a warm-up for us to go over stuff, but it will mostly be a day for you to work and get your homework done. So that's going to be it. Like your Unit 2 quiz is only going to cover basically your derivative rules and then this idea of the tangent line. We only actually have one more topic to learn after the quiz, and that's going to be another derivative rule called the chain rule, but it's a little bit more complicated, so I didn't want to put it on this quiz and just kind of save it for the test. So if you're good to go, feel free to go ahead and sign out of the live portion of the meeting. If you want to hang back and ask any questions on any homework or anything like that,